Hello all, thank you for attending this session called Finite Element Analysis on Biofuel Particle Dispersion. Here's a brief summary of what we're going to talk about. So a brief introduction, then the governing equations, next the finite element analysis itself, then the semi-Lagrangian formulation, and finally I'll present the results and conclude the work. Biofuel is the energy source obtained from biomass, so it's a clean source of energy. And it also, as shown by these works I've highlighted here, can decrease particle and gas pollutants emissions. So by means of this work, we have the physical problem, which is biofuel particle emission, and we'll transform it into math models, which are ordinary differential equations and partial differential equations, and solve it by means of the finite element method and other discretization, like the semi-Lagrangian one. And finally, we obtain the algebraic equations. This is done by means of the finite element analysis called FEA, and we use the Euler-Lagrange one-way coupling, which means only the solid phase suffers influence of the fluid. Here's the introduction of the governing equations, which is basically the Navier-Stokes equations in the non-dimensional form. Here it's modified to aggregate the expansion problem and also the advective problem. For the advective problem, we have the Galileo number and the Grashof number for the temperature gradient. And for the expansion problem, we have the Reynolds number. So for the advection problem, the Reynolds number is set to 1. And for the expansion problem, we have the Grashof and Galileo set to 1 or 0. And also, here is the term responsible for buoyancy, which multiplies the gravity. And here are the dimensionless groups. We have Reynolds, Prandtl, Galileo, and Grashof. We also have here the continuity equation for incompressible flow, and also the energy conservation, for which we determine the temperature field. For the solid phase, as we see in Borello and Griffith, it's basically Newton's second law of motion. Have the mass of particle multiplied by the time derivative of its velocity equals to the sum of the forces acting in the particle. We get to the finite element analysis through the variational form. The variational form is basically multiplying the equation by their respective weight and integrating in the domain omega. The weight for velocity is W. The weight corresponding to pressure is K, and the weight corresponding to temperature is R. So here is the variational form of the Navier-Stokes equations. And we also applied the Green theorem for the second derivative terms. So we have this term here. And since we have homogeneous Neumann and Dirichlet conditions only, we have no integration in the contour. So we have only the integration in the domain. Here we present the elements used. On the left-hand side, we have the mini element, which is the simplest element that can be used to satisfy the LBB condition, which is the condition that needs to be satisfied for a saddle point problem, such as the Navier-Stokes one. And on the right-hand side is the quadratic element. We see 1 point for each side of the triangle. And here are the interpolation for the discretization of the variables like u for velocity, P, pressure, and T, temperature, and their respective weights. Since we do not use the linear element, here we have the shape functions n as a function of L, which are the linear element shape functions. So here we have matrices of the finite element analysis. We have M, K, and G for mass and stiffness and gradient. And we also have M star and K star for temperature, since we use the linear element for its calculation. Finally, we'll have the semi-Lagrangian formulation, which is the discretization of the material derivative through a first order time scheme. We already have the second order space approximation for the quadratic triangles. And this is an unconditionally stable scheme. So here you have psi can either be U or temperature, for example. And D, the D subscript is respective for the value of that variable on the previous time step at the place where that particle actually occupied. So here in this scheme, we have X and X underline D. So this is the place where this point of fluid was in the previous time step. So we have psi D is the temperature at that point. So this is the material derivative in the discrete form. Finally, we get to the algebraic equations, like the system of equations. We have two system of equations. They seem uncoupled, but if we notice the subscript D here in temperature is responsible for coupling those system of equations, since we need velocity to determine the time derivative, the material derivative of temperature. So we have two systems to be solved. Here's the first result as validation from the literature of the lid-driven cavity. We plot a vertical line here, for which we plot the horizontal velocity, and we compare with the literature, and we see that the points are quite close to the ones from the literature. Next, we plot the horizontal line and plot the vertical velocity along that line. And again, we compare with the literature, and results very encouraging. So finally, the expansion with particles with a more complex geometry. So here I present the scheme of the contour conditions and also the dimensionless groups, Reynolds, Froude, and Prandtl. We have a velocity entering in of the unit, and we have no slip conditions on the walls and prescribed pressure at the exit. And we have 3 cylinders in the middle. Here you have the mesh and also the characteristics of that mesh. So it's a 1,626 element mesh, 2,509 nodes, delta T of 0.1, 300 iterations, 3 seconds per iteration, 50 particles of 0.01 non-dimensional diameter, and a density of 7. Here are the results. So we see that for the high Reynolds number, we have recirculation regions here and here. So the fluid passes through the cylinders, and we have recirculation before the cylinders as well. And if we can look at this video here, particles get trapped in this recirculation. Most particles keep recirculating, and that is an interesting mechanism of reducing emissions. And also some other particles get trapped in the recirculation after the cylinders. and some of them get passed. So depends on how light particles are, of course. And this is a very interesting result to be shown. Well, as a conclusion, the finite element method presented here was satisfactory, and particles behavior was qualitatively accurate as what was expected to particles in fluids. And we validated the method, and we see that it's able to simulate particle emissions and their interaction with obstacles, and also an optimization of the code is on the way, and some of it has already been concluded to simulate finer mesh in more complex cases, like 3D cases, for example. Thank you very much.